Hey, it's me again. Just go and grab some water before I continue. Yes, then as I said, I will try to explain a bit more of the gas law this particular video. And before I continue on, there's a three graph that you will need to familiar with. The first one is about the pressure and the temperature. So let's say we've got the pressure here. Maybe pressure and the volume first. Always like to do pressure and the volume. Then the second one is the pressure and temperature. And the last one is the and the last one is the volume and the temperature. So as you can imagine, pressure and volume, as I said previously, is about inversely proportional to each other. That means the higher the pressure, the increasing of the pressure would be the opposite effect for the volume. It is the lower the pressure. So if you're looking at that, you expect that the low pressure would be a high volume right there. The low pressure, the low volume would be high pressure there. And you will find that the graph will look like this. It's like a curve coming down. It's a parabola graph, a quadratic graph, or you can say. And that curve has a particular fact that if you have the pressure here, P1 and V1 there, or the other way around, because I'm using volume as a V as a X value and P as the Y value. Then you will have the V2 and P2. As you can find that P1 V1 equals to P2 V2, a square can be formed by draw under the graph. Let me find the square. So if you try to draw a square here, right from from this point all the way down here, that you form one rectangle, and this rectangle is the P1 here times by V1, and that area would be exactly equals to, I'll use the other colors on this side, use the green one highlighted the area there, and this area refer to the V2 and P2 would equals to the area regarding the V1 and P1. So that's basically where the formulas come from by looking at the graph. And then the second graph and the last graph is way more straightforward. What do they look like? Straight line and a straight line. As you will remember what I said before, increasing the pressure basically accompanied with increasing the temperature. The higher the temperature, the higher the pressure. And then the higher the temperature would give you the higher the volume. So that's basic fact that we always know. And this is called directly proportional to each other. And the formula can be written by P1 T1 equals to P2 T2. So if you're using one divided by the other one would be equals to the one divided by the other one. It always like this if you're looking at a kind of like mathematical values. So those three graphs, bear in mind that you always need to notice it. And I also asked you to do some question about Boyle's law and Charles' law. Both of them is related to you. I'd like you to identify those graphs, those names, those two laws with those two graphs. Right? What else do I need to pay attention on this? Yeah, the other thing that you need to pay attention to those two graphs is the temperature. The temperature starts from 0 K. Okay, there is 0 Kelvin. Right? And at this point there, is the absolute zero Kelvin. Okay, 0 Kelvin. So if you're talking about both pressure and the volume, would come down to kind of nothing, close to 0 pressure and close to 0 volume at absolute 0. So that is the theoretical conditions that you would never be able to achieve it. So yeah, it's just a theory, and I don't think we would ever find absolute 0 myself. Yes, next one is all about pressure. As pressure is one of the most diverse kind of measurement unit, you will see among those three factors, people around the world using all different types of unit. As I say, there would be the most common one is called kPa, kilopascal. And then you will also find one of them called ATM with atmosphere. And the third one is called mmHg, is millimeters mercury. Each one of them has a kind of its history. And I don't like to talk about history in the video. I'd like you to go and find it yourself. I'm not good at this at all. But I can assure you, kilopascal, basically all three of them need to have one thing in common, which is what would be at sea level, what would be their values. So at the time, at sea level, all three of them would refer to have three different values, but exactly refer to the same conditions. So there would be the same conditions applied on those three. At the same condition, which is at the sea level, we also call that one ATM, 1 atmosphere. So now what we are experiencing, no matter like in Hong Kong or in Australia, there's still ATM, 1 atmosphere. And for each atmosphere is equal to 101.3 kilopascal, 101.3 kPa. And for each atmosphere is equal to 760 millimeters Hg. There's history behind that, and yeah, don't care about that now. But like yeah, those three you need to be able to convert from each other. I do find some exercise online, not this one, this one. So there would be quite a few of them that you'll see. For example, the questions here saying that the air pressure, the air pressure as a tie is 109 kilopascal. What would that be in atmosphere? So in atmosphere and kilopascal, 109 kilopascal. If we have 109 kPa, 101.3 is equals to 1. 109 is slightly bigger than 1 ATM. So what do? You can basically change that by saying 109 divided by 101.3, and you should have that straight away. Easier to do that. So 109 divided by 101.3. We've got 1.076, maybe 1.08 ATM. S has three significant figures, right? So that's very simple to convert from atmospheres to from kilopascal into atmosphere, right? Then you can also try to change that into say like millimeters mercury. Millimeter mercury for each of the ATM is 760. Then 1.08 times by 760 would equals to our answer times by 760 is equals to 817 is more than enough because these three significant figures that we need to round these up. It should be 818. Then I will write down MHG. That's our answer. Right? So it's easier to convert from like if you need to say, oh, what do we do if I want to do kilopascal into millimeters mercury? Then you need to convert kilopascal into 1 atm first, and then times it by that. That would be much easier than just like getting a lots of different formulas together. There's a few more questions that you can do. That's the answers. Which one is good? Maybe that one there. Question 5. Let's chop this one. So question 5 there is talking about a bag of potato chips near the sea level. the pressure is 761. 761 is slightly higher than 1 atmosphere. Then how can you convert that into Pascal or kilopascal? Kilopascal means 1,000 Pascal, so it doesn't really matter too much. It's like gram or kilogram, so you can just 100 times different. What do you do to do that? Definitely the first thing you do is to convert that into 761.3 out of 760. That is probably 1.00 something as an ATM. Then for the atmosphere, you want to change it into Pascal. You times it by 1 atmosphere is equals to 101.3 kilopascal. Yes. Then to change kilopascal to a Pascal, you times it by 1,000. So the answer would be 761.3 divided by 760 times it by 101.3 and then times it by 1,000. And I have the answer is 101,473. 101,473 PA. Right? Let's see whether I'm right. I'll check the answer. This is not. I didn't write this one at all. So I just copy this online. So for the question 5, a potato one, 761 divided by 760 times by 101.3 times by 1,000 equals to 101,743. 101,743. Right? So if you want to find out more formula, you can go online, do all the formulas. But this is the way of thinking. It's all about the same condition, which is 1 atmosphere. Then you just convert between each other by using that core the core connections between those units. Right? So this is about the pressure, and hopefully you'll find that helpful about doing all this. Then the last thing that you would come encounter would be saying, what if I have everything combined together with those gases law? So let's say I will have a question saying a reaction. So they're always about reactions. I love this reaction. You know that I have been using this all along the years. Nitrogen with hydrogen gas and I have just trying to put 2 there, 3 there, and 2 there. I like this reaction because it's all about gases. The other thing is 1, 3, and 2. So you have 3 different ratios between each other. So if you're looking at this, nitrogen gas react with hydrogen gas, making ammonia. Then, what if I like to say 20 liters at 50 degrees Celsius? Okay, and then the pressure is at 1 atmosphere. I'd like to find out, so I have 20 liters with 30 liters at the same temperature for both of them. And how much gases would I be able to produce in terms of ammonia at the same temperature and pressure? Right? So this is why do we need to study gas law, is try to apply those concepts into equations. And without applying those concepts into equation is physics. But when you start doing that into a chemical reactions, that comes to chemistry. Now we say we know about the equations, and you should be able to remember this by now. Is PV equals to nRT. Pressure times by volume, right there. We've got pressure is 1 atm. Atm is not the proper way to do for the equations. We have to change it into kilopascal. 1 atm is equals to 101.3 kPa. Right? And then volume, we use liters. 20 liters, perfect. What do we have in terms of T? Temperature is 50 degrees. When it's 50 degrees, we have to change it into Kelvin. Is 323 now. 50 plus 273 in terms of Kelvin. For 30 liters, pressure exactly the same. So you would expect that would be a little bit bigger values if you times it together. The volume is 30 liters. Temperature is 50 plus 273 equals to 323 K. Now, what do we do in terms of it? If you do have the pressure, let's highlight this. If you have the pressure, you have the volume as well as the temperature, and R is always the constant, equals to x.31 as long as you use the right unit for all the other three. Then what is the one that we can find out would be the little n there. Little n stands for number of mole. And the number of mole would be, let's try to find out, the little n's here would be equals to PV over RT. And this little n here would be PV divided by RT, which is 101.3 times by 20 divided by 8.31, and that one is 323. That is 101.3 times by 30 liters divided by 8.31 times by 323. For the calculators again, I like to use scientific then. At least we need to have a bracket for scientific one. And what else do we do? 101.3 is 101.3 times by 20 equals to that. It's divided by a bracket 8.31 times by 323 close bracket, and it's equals to 0.7548, which is 0.7. The number of mole is 0.755 mole as the answers. Then we have the other one, which is doing exactly the same. 101.3 times 30 divided by open bracket, and that's 8.31 times 323, close it, and equals to 1.13. 1.13. Both of them I use 3 significant figures. Right? Now, if I have that, the ratio is 1 to 3. The ratio is 1 to 3. That means I do need more hydrogen to react with. One part of hydrogen is need 3 times more than nitrogen, which is every 1 part of nitrogen require 3 parts of hydrogen gas. If you say there's a 0.7 there, 0.7 times 3 is 2.1 already. So you don't have 2.1 mole of hydrogen gas. So I can very quickly say this is the limited reagent straight away. So don't ask me about limited reagents. You should know it. The limited reagent is the one that is not enough. It's going to react completely. And then if we say 1.13 is going to react completely, so that means 3 times less of nitrogen is going to react, and the rest of them is going to be left over. So 1.13 divided by 3 would give you 0.376 or 0.377 mole. It's going to react, and because this nitrogen gas would be the one that in excess, 0.755 take away 0.755, then I will have roughly 0.39 or 0.38 mole that's sitting there. Half of them is being sitting there and doing nothing. Right? That's perfect. Half and half. I don't know why I just make these values up and it looks really good. Then the question is not saying like how much you're going to react. The question is always asking you the product. How much product are you going to produce at the end of it? Then we know that if we do equations, always look at the limited reactions or limited reagent, then look at the ratio. The ratio between the hydrogen gas and the ammonia is the coefficient, which is 3 to 2 ratio, is always 1.5 times difference. Right? Hydrogen is 1.5 times more than ammonia, or ammonia is 1.5 times less. So what is 1.13? 1.13, and is divided by 1.5 because it's 1.5 times less. Right? Make sense? Then I will have 0.753 mole. So the good thing is, looking at the mole ratio, we are very easy to find the answer. Changing the red, please. So that 2 ammonia giving you is 3 to 2 ratios, and is 0.753 mole is going to produce at the end of it. Right? At the end of it. But is this one the right answer? No. I'm very clear saying that how much in terms of liters, not how many liters are you going to do, and 0.753 is not liters. Then once we've got the number of mole, we should try to change that into volume by the same formula. PV equals to nRT. As I say, pressure doing exactly the same, 101.3. Then volume is the one that we want to find out. Number of mole is, can see 0.753, and R is 8.31, and the temperature keep the same, is 323. Everything is being valued there. Basically, V is equals to 0.753 times it by 8.31 times it by 323 divided by 101.3. Most of the students won't have any problem understanding equations, but they have the problem understanding the mole ratio, and I believe you're fine with it. Then now let's do the values. Is 0.753 times it by 8.31 times it by 323 all together, then divided by 101.3. Now the answer is 19.95. 19.95 give me about exactly 20 liters in terms of significant figures. 19.95 liters. Round this up, 3 significant figures is 20.0 liters. I will produce 20 liters at the end of it. This one is 30 liters. You will find that very easy. If you convert the first one there, it will use 10 liters of nitrogen gas, react with 30 liters of hydrogen gas, produce 20 liters of ammonia. Write this all again. You'll find Gass's law are interesting. N2 plus H2, according to the ratio, is 1 to 3, going to make 2 NH3. We have 10 liters. Let's go react with it, because 20 liters, 7.755, we just used half of it, 1377. And then completely 30 liters is going to react, and at the end we make 20 liters. In terms of number of mole, it shows that for all the gases reactions, if you are able to keep them as a same temperature and the same volume, not same volume, sorry, same pressure. What I'm doing, stupid me. Not, can't be volume, because like 10 and 30 already. If you be able to keep the whole system, as I say, the whole system like can be, so the things that left hand side, right hand side, then you'll find that the number of mole is basically can be used. The number of mole is directly equals, not equals, but you can tell the volume straight away. And because the volume control the number of mole, if there's like under the same temperature and the same pressure, then all you need to do is to look at the volume, and you can tell the ratio of volume by finding out the answer straight away. So instead of going through all the number of mole here, then what I need to do, I just need to say 30 liters has more number of mole than this, is 1 to 2 ratios. Then 30 liters is going to react with 10 liters of nitrogen gas and make 20 liters straight away. And I can skip all the steps in between them. Gass's law. So this is why we say, yeah, understanding will help you out, like just to kind of like skip the whole thing in between. So you ask me like, what if the temperature difference or something different? No. If the temperature is different, you have to go through all the steps right there. There's no other way. You can kind of like the shortcut. There's no shortcut between them if the temperature or the pressure change in before and after the reactions. But like, yeah, I would say most of the time reactions would stay the same just to please you as a Year 12 student. Now, so what we do, this is a shortcut for doing that, and there's another way saying this as well. What the other thing that we have to focus on in this particular way is a conditions. In previous syllabus, there's a 2 conditions we need to discuss. One is called standard temperature and pressure. The other is called standard lab conditions, STP and SLC. Both S stand for standard, and T is temperature, and P you find that basically called pressure. Standard temperature and pressure. Standard L is a lab condition, laboratory. I don't want to laboratory condition. It's too hard to spell. Laboratory standard lab conditions. When you look at standard lab condition and STP, STP used standard water freezing point 0 degrees as a standard temperature, and the pressure is 1 atm, which is 101.3 kilopascal. Right? And the standard lab conditions, we won't change the pressure, but no one would like to work at 0 degrees. So probably room temperature is what we're looking for. And the room temperature is about 25 degrees. It's what we like the most. So why do we need those, like we set up a standard pressure or standard lab conditions? Then you would be able to tell a reactions. So N2 plus H2, 3 of them turning into 2 of them there. If I say, yes, I do this one at a STP condition, and before and after they all STP, do you need to measure temperature again? Do you need to measure pressure again? You don't, because well, when I say at STP, we all understand it's 0 degrees and 101.3 kPa, and we save lots of time by doing that. It's like every single time do a reaction, we need to measure temperature, measure pressure. If we just say at STP or at SLC, we skip all the writing straight away. So that means 10 liters would react with 30 liters and produce 20 liters of ammonia at STP. It will be the same thing at SLC. 10 liters react with 30 liters and make 20 liters. Nothing else. That's it. That's straight away. And we will find one thing. Do you have exactly the same amount between STP and SLC for 10 liters of nitrogen gas or 30 liters? You expect that if you have the same pressure and same temperature, it would be the same amount. But between STP and SLC, there would be a slightly different between is 0 degrees and 25.55 degrees. Then you propose the amount in between there would be slightly different, a very small scale. How do we prove it? PV, N is equals to PV over RT. N is equals to PV over RT. Using 10 liters as an example, if there's a 10 liters there, pressure is 101.3 times by 10 over 8.31 times by 0 degrees is 273. While you have exactly the same except 0 degrees become 25 degrees. That's 101.3 times by 10 liters over 8.31 times by there is 273 plus 25. 273 plus 25 equals to 298. 298. Then we find the answer by putting that into the calculator. It's annoying every time I need to do this again. (101.3) times by 10 divided by 8.31 and then divided by 273 is 0.447 molar. Yes. Happy? Then the other one is 101.3 times by 10 divided by that one, 8.31 times 298 close 0.709. Right? Does it make sense to you now? For 10 liters of nitrogen gas, if you use it at STP, 10 liters of nitrogen gas, it has 0.447 mole in it. Exactly same liters of nitrogen gas, because gases expand when it's higher temperature. You would expect that the same volume would have slightly less number of mole in there. And since the and nitrogen gas, no matter it's nitrogen gas or hydrogen gas or ammonia gas, if they do it at the same temperature, at the same STP, they all will be like 0.447 mole. It doesn't matter whether it's nitrogen gas, hydrogen gas, or ammonia. But the only thing that actually pay attention we need to for about gas law is the conditions. Even though they both 10 liters nitrogen gas, they would have different number of mole between two different conditions. So hopefully it makes sense to you. What happened, I like to say, is if you have 10 liters of hydrogen gas, it equals to 0.447 according to the gas law. If you have 10 liters of ammonia gas, it also equals to 0.447. Right? The conditions determine the number of mole for gases according to gas law. However, if you put 10 liters of hydrogen gas, if you find 10 liters of hydrogen gas at SLC, it would only be 0.409. For 10 liters of ammonia gas, it would be 0.409. If you put 0.409 10 liters of hydrogen gas and try to freeze it and put it into the 0 degrees, then you would not have 10 liters anymore. It would be 9.8 or 9.7 or whatever. It would drop a little bit because you only have 0.09 mole there, and then it would drop the volume. Right? So that is what we like to do for gas law. And because of this gas law, then, and those two conditions is universal, then we can use this particular way to find out two values. And the two values, we call them molar volume. And the molar volume in year 12, suppose in all syllabus, you need to remember both STP and SLC. But you're lucky now, SLC is the only one that bother us in year 12. Then, what would be the molar volume when number of mole equals to 1 mole? What? And then, what would be the volume that contributes to it? PV equals to nRT, number of mole equals to, or not number of mole, V equals to nRT divided by P. 1 divided times by 8.31 times by, what is the temperature at SLC? The temperature is 25 degrees, means 298. So we times by 298 divided by, the pressure is 101.3, 1 atmosphere. 8.31 times by 298 divided by 101.3 is 24.45. Or you can say 24.5 liters. As a molar volume at standard lab conditions. Right? And please remember this, 24.5 as this, or 24.45 as this is the one that you need to use quite a lot when you see any of the gas law equations or gas law questions. By dealing with this, you can apply a new number of mole reaction, because number of mole equals mass over normal mass. Yeah. But this one only apply on solid or something that you measure, you can weight. But what if I only give you gases? And because gases at the same conditions is directly related to the volume, then number of mole can be calculated by the volume given divided by the molar volume. Right? Hydrogen gas. If I give you 2 grams of hydrogen gas, you can do hydrogen gas 2 grams is 2 divided by 2. Number of mole equals to, you got 1 mole, mass over molar mass, straight away. But what happens if I give you, say, I give you 50 liters at SLC? Then how can you find the number of mole? You couldn't get this. You couldn't try to like look at this to weight it. You can't weight it because it's flowing in the air. How can you weight it? You can't. If you can't weight it, what do we do? Molar volume. Number of mole is equals to volume given, just like the mass given there, divided by molar volume, 24.5. So 50 divided by 24.5 give you 2.04 mole. You have 2.04 mole straight away, a molar volume. So we need to apply the molar volume concept and then the gas law into the question that we're going to do in the near future. Right? So hopefully you understand it all. It's a long class, but like to be able to try to explain this is difficult. I'm supposed to have 2 weeks in year 11, but I only have 2-3 class to explain it. But like hopefully you enjoyed doing more of this, and try to do a question now. Thank you.